Differential pair. The versatility of differential pairs and their expense and their extensive use in analog systems motivate us to characterize their frequency response for both differential and common mode signals. Consider the simple differential pair shown in figure A with the differential half circuit and the common mode equivalent circuit depicted in figures B and C respectively. For differential signals, the response is identical to that of a common source stage, the exhibiting Miller multiplication of CGD. Note that since plus V into by 2 and minus V into by 2 are multiplied by the same transfer function, the number of poles in V out by V in is equal to that of each path rather than the sum of the number of poles in the two paths. For common mode signals, the total capacitance at node P in figure C determines the high frequency gain arising from CGD3, CDB3, CSB1 and CSB2. This capacitance can be figure A differential pair B half circuit equivalent C equivalent circuit for common mode inputs. Quite substantial if M1 minus M2 M3 are wide transistors, for example limited voltage headroom often necessitates that W3 be so large that M3 does not require a large drain source voltage for operating in the saturation region. If only the mismatch between M1 and M2 is considered, the high frequency common mode gain can be calculated with the aid of equation. We replace R03 with R03 1 by CPS and RD by RD 1 by CLS, where CL denotes the total capacitance seen at the each output node. Thus AVCM is equal to minus delta GMRD parallel 1 by CLS by GM1 plus GM2 R03 parallel 1 by CPS plus 1, where other capacitance in the circuit are neglected. This result suggests that if the output pole is much further than the origin, then is the pole at node P, the common mode rejection of the circuit degrades considerably at high frequency. For example, an illustrated figure, if the supply voltage contains high frequency noise and the circuit exhibits mismatch, the resulting common mode disturbance at node P leads to a differential noise component at the output. Figure effect of high frequency supply noise in differential pairs. We should emphasize that the circuit of figure A suffers from trade-off between voltage headroom and CMRR. To minimize the headroom consumed by M3, its width is maximized introducing substantial capacitance at the sources of M1 and M2 and degrading the high frequency CMRR. The issue becomes more serious at low supply voltages. We now study the frequency response of differential pairs with high impedance loads shown in figure A. is a fully differential implementation. As with the topology of figure, this circuit can be analyzed for differential and common mode signals separately. Note that here CL includes the drain junction capacitance and the gate drain overlap capacitance of each PMOS transistor as well, also as depicted in figure B. For differential output signals CGD3 and CGD4 conduct equal and opposite currents at node G, making its node an AC ground. In this practice, node G is nonetheless bypassed to ground by means of a capacitor. The differential half circuit is depicted in figure C with the output resistance of M1 and M1 and M3 shown explicitly. The topology implies that equation can be applied to this circuit if RL is replaced by RO1 parallel RO3. In practice, the relatively high value of this resistance makes the output pole given by R01 parallel R03 CL power minus 1 the dominant pole. We return to this observation in chapter. The common mode of behavior of the circuit is similar to that of figure C. Let us now consider a differential pair with active current mirror. How many poles does this circuit have in contrast to fully differential configuration of figure A? This topology contains two signal paths with different transfer functions. The path consisting of M3 and M4 includes a pole at node E, approximately given by GM3 and C, where C denotes the total capacitance at E to ground. This capacitance arises from CGS3, CGS4 and CDB3 and CDB1, and the Miller effect of CGD1 and CGD4, even if only CGD3, CGS3 and CGS4 are considered. The severe trade-off between GM and CGS of PMOS devices results in a pole that greatly impacts Here you can see in this figure A differential pair with current source loads, B effect of differential swings at node G, C half circuit equivalent. Figure high frequency behavior of differential pair with active current mirror. The node path, the performance of circuit, the pole associated with E is called mirror, a mirror pole. Note that as the circuit of figure A, both signal paths shown in figure contain a pole at the output node. In order to estimate the frequency response of the differential pair with the active current mirror, we construct simplified model depicted in figure A, where all other capacitances are neglected, replacing V in M1 and M2 by the Thevenin equivalent. We arrive at the circuit of figure B, where from analysis of figure Vs equal to Gm Vx is equals to Gm n R naught and V in, and Rx equal to R naught, and here the subscript P and N refer to P and N refer to PMOS and NMOS devices respectively. Figure A simplified high frequency model of differential pair with active current mirror. B circuit of A with Thevenin equivalent, and we have assumed 1 by GMP very much less than ROP. The small signal voltage at T is equal to V out minus Vs 1 by CES plus GMP by 1 by CES plus GMP plus RS, and the small signal drain current of M4 is GM4 VE, nothing that minus GM4 VE minus VS is equal to V out CLS plus R naught P minus 1. We have to the power minus 1 V out by V in equal to GM R naught N 2 GMP plus CES by R2 R naught P R naught N CECLS square plus R naught N plus R naught P CE plus R naught P plus 1 plus 2 GM plus 2 GMP R naught N CL S plus 2 GM R naught plus R naught P. Since the mirror pole is typically quite higher in magnitude than the output pole, we can utilize the results of equation to write omega P1 is similar to 2 GMP R naught N plus R naught P by 2 R naught N plus R naught P CE plus R naught P 1 plus 2 GMP R naught N CL. Neglecting the first term in the denominator and assuming 2 GM P R naught N is greater than 1, we have omega P1 is similar to 1 by R naught N parallel R naught P CL. An expected result, the second pole is then given by omega P2 similar to GMP by CE, which is also expected. As interesting point revealed by equation is a 0 with a magnitude of 2 GMP by CE in the left half plane. The appearance of such 0 can be understood by nothing that the circuit consists of a slow path M1, M3 and M4 in parallel with a fast path M1 and M2 representing 2 by A naught by 1 plus S omega P1 plus 1 plus S by omega P2 and A naught by 1 plus S omega P1 respectively. We have V out by V in equal to A naught 1 plus S by omega P1 into 1 by 1 plus S by omega P2 plus 1 is equal to A naught 2 plus S by omega P2 by 1 plus S omega P1 into 1 plus S by omega P2. That is, the system is which 0 at 2 omega P2. The 0 can be absorbed by the method of figure. Comparing the circuits of figure A and B, we conclude that the former entails no mirror pole, another advantage of fully differential circuits over single-ended topologies. Thank you.